Welcome guys. In this video we are going to solve a well-known problem of LeetCode related to binary search trees. It is a very nice problem for those who are beginners in binary search tree, those who are learning binary search tree data structure. So basically a binary search tree, who don't know, is a hierarchical format of storing data in which we have nodes, different nodes. For example, this is a binary search tree. As you can see on the screen, a binary search tree have many nodes and each node has only two child, and that's why the name is binary search tree. Binary means two. As you can see in this binary search tree on your screen, 25 has two nodes, 20 and 36, and these two nodes which are connected to 25 are the child nodes of 25, and 25 is known as the parent node of these two child nodes. In this whole binary tree, 25 comes at the top. It is the head node of the tree, and other are the child nodes for 25. In similar way, in our right subtree, which is this, we have 20 as the head node, and 20 is the parent node of 10 and 22. And here at the last we have 5, 12, 28, 38 and 48. These are nothing but the leaf nodes of our binary search tree. That is, they don't have any children. They are the last nodes. For making a binary search tree, we have many rules to be followed. The rule is that while making binary search tree, our left hand child node's value should always be less than the head's value, and the right hand child's value should always be greater than the head value. For example, in this particular problem, as you can see, 25 is the head node of 20 and 36, and 25's value 25 is actually greater than 20, meaning the left hand child, which is 20, is actually less than the head value, which is 25, and 36, which is the right child of 25, is actually bigger in value than the head node, which is 25. In similar way, in a left subtree, we have 20 as the head, and 20 is actually greater than 22. 20 is actually greater than 10, which is the left child, and is less than 22, which is the right child. In similar way, this should be true for recursively for all the nodes of the binary search tree, and then we can say our binary search tree is ready. So now let's move on to the traversal method of the binary search tree. So basically a binary search tree is traversed in many ways we want, but the most interesting way or the most efficient way for our problem of LeetCode would be in order traversal. So what happens in order traversal is that we traverse the binary search tree from left to right. Starting from the left node to the right node we go, and whichever traversed order we get is always in ascending order. For example, for this particular tree, in order traversal, first if we go from 25, it will first go to 5 number node, and then it will go to the head node, which is the parent node of this node, and then it will go to 12. And similarly, after 12, as it doesn't have any child, it will go to 20, and then it will go to 22, and similar way this will go on, and ultimately it would be like 25, then 28, then 30, 36, 38, 40, 48. And in this way we are going to get an ascending order of the values of our nodes of the binary tree. So to write the binary in order traversal of this binary tree, we would write it as, let's write it now. Over here, so if we see our binary search tree, first we have 5 as the node, which is least in value. Then we will go to 12, then we will go to 10 actually, sorry, then we will go to 12, then we will go to 20, and then 22, then 25, then 28, which is here, over here, 28, then 30, 36, 38, 40, then 48. So let's write it over here again. Then we have 30, then 36, then 38, then 40, then 48. So this is the in order traversal of this particular binary search tree. Now let's see what our problem says, and let's try to understand our problem. So this is our problem. The problem statement says that we are given a root of the binary search tree where exactly two values of the nodes of the tree were swapped by mistake, and we have to recover this without changing the binary tree data structure. So for example, as they have given over here, we have given this tree which has 1 as the head node. For 3 is the left child and right child is absent, and for 3 we have right child and left child is absent. But the problem in this tree is again that the parent child is 1 and the left child for this parent child is 3. However, we wanted parent child value to be greater, but here we can see that 3 is actually greater than 1. We would actually want here 1, and over here we have want 3. So the real binary tree, which is the corrected binary tree, would be 3 over here and 1, 1, 2 over here. Similarly, if we see another example over here, 3 and 2 are swapped and we have to recover this. So the recovered binary tree would look like this. They have given the input and the output to know us, and we have given the constraint that the nodes are in range of 2 to 1000. And yeah, now to approach this problem there are actually many ways. The one way would be that we would be first traversing our binary tree in order form. After traversing it, we are going to actually sort the array that we got, and then we will recover the binary search tree. But the problem in this approach would be that it would take much time complexity. Actually, it is going to take a complexity of O of log n square, which is actually not efficient. To solve this problem in O of n time complexity, we would use a different approach, and also we will use an approach which uses the space complexity as O of 1. So let's now understand the approach. So for this problem, what we are going to do is that, let me erase it first. So we are, for this particular problem, we are actually going to initialize 3 particular variables. We can say them as pointers. The pointers will be the second, first and the previous. As we traverse our binary search tree in order form, we are going to initialize these variables. The previous variable will actually going to store the node which we visited earlier. For example, if we start from the 5, then we go to 10, then for this traversing, we will have the previous pointer, or this previous pointer, which is this, to be pointing over to the 5. then and our node will be 10. Okay, after we go to 12 from 10, our previous pointer will now point 10. In this way we are going to store the value of the previous node that we visited in the previous pointer. And then for the second and the first pointers that we have made, these pointers will be useful to help us to swap the two numbers. Now for this we are actually going to swap this 12 and 48 for this problem, just to understand. Let's swap them. Let's swap this too. So now 12 and 48 are swapped for our problem, just for understanding. Okay, any node can be swapped. Okay, so now the problem will be like this, that we will first as per the in order traversal we will go to phi, and then at this particular level, that is the phi, we will not have any previous value. Our previous will set to none, as we have not visited any node previously, and our first and second pointer will remain none as well. Then we will go to 10 and our previous pointer will now point to 5. Then we will now check if the node's value, as we are now at 10, that is our node. So if we will check if the node's value is actually greater than the previous value. For example, over here 10 is actually greater than the previous value, which is 5. So if this condition satisfies, it's okay. We will go continue our in order traversal. Then we will go now to 48 and our previous value will now become 10 and our node's value will now become 48. We are now at 48. Okay, so when we are at 48, again we will check if the node's value is greater than the previous value. As you can see over here, 48 is greater than 10, so it's all okay. We can proceed further. Now we will now approach to 20 as over here, as we don't have any left child and right child for this 48 node. Now our previous pointer will now again point to 48 and our node will be at 20. So let me have this over here. So this is our node and our previous pointer is at 48. So when we are at 20, we will now check if 20 is actually greater than the 48. And here is the problem. We got exception, that is we got our swap node. Here 20 is actually less than 48, but the situation should have been like this, that we should have had here the value greater than 48, but we don't have. And this is the point we come to understand, that we have got the first node which is swapped. So now what we are going to do is that we will take the first variable and we are going to initialize this first variable to this previous value, and our previous node will now become 20, and we will traverse further and we go to 22 and the 22 becomes our node now. So now we will further go on, and also we are going to, at the same time, when we have encountered our first swapped node, we are going to initialize the second pointer to the 20, which was our node. Okay, so now we will traverse again. Now we are at 22. We will check if 22 is greater than 20, which is the previous value. It's greater. Okay, we can now go to further. Now we will go to 25 and we will check if 25 is greater than 22, as our previous pointer will now point to 22, and it's all good. In this way, 25, we are going to go to 28 as per the in order traversal, and our previous value is 25 only and our node's value now becomes 28. Now we will check if 28 is greater than 25. It's true, then we will proceed further. Now our previous pointer will now point to 28 and our node's value will be 30. We will now again check if 30 is greater than 28 and it's greater. Then again we will have previous pointer pointing to 30 and our node's value will now become 36. And 36 is greater than 30. That's true. And after 36 we are going to go to 38 and we will again check if 38 is greater than 36. If yes, we are going to go further. Now our previous pointer will now point to 38 and our node's value will now become 40, and 40 is greater than 38. Now our previous pointer will now go to 40 and our value of node will go to 12. Now again we will check if the node's value 12 is greater than 40, and here we again encountered a problem that 12 is actually less than 40. And here is the stage at which we found our second swapped node. At this point we will initialize our second variable, which was over at 20 to 12, keeping the first variable intact at 48. And now what we are going to do is that we are now going to swap these two nodes. We are going to assign the first value to second and second value to the first. So this was the logic. Now let's see how we can write it using Python in code. Let's go to our code block. Okay, so here we have the recover tree function already made. Now we have to write. First, our step is to initialize the 3 pointers, which are first is equal to second is equal to previous, which is equal to none. Now we will make our in-order function defined in order, and it is going to take the root value. They have already provided us the root. Then put here node. Then we will access this first, second and previous variables by using non-local keyword. Non-local previous comma first comma second. Now it's time to use recursion to go to the leftmost child and traverse the tree. We will say if not node, we will just return up, and for recursion we will say we will call the function again by doing in order of node dot left child to make the left in order. After doing this, we will now check the condition for our previous value and the node's value. So we will say if previous exists and if previous dot value is greater than node dot value, and if this happens we have got the node which is swapped. Then what we will do is that we will say if not first, that is if the first variable is not initialized, that is it is none. What we will say is that we will store the first value as previous value, and then we will initialize the second pointer outside it. Second is equal to the node's value. Then outside the if condition, for traversing we will say previous is equal to node. Then we will traverse our tree in right side. We will say in order again and pass node dot right child, node dot right. Then we will now come out of our traversal and we will call this in order method by passing the root that we have been given, and then we will assign will now update the nodes values which we are going to swap. that is the first will be first dot val comma second dot val will now be equal to second dot val comma first dot val. So what we did here is that first we actually initialized our variables, that is the first, second and the previous. Then we defined our in order function, and in that we actually recurse our binary search tree for in order traversal method. Then we check if the previous value is greater than the node's value. If that happens, we store the first variable's value to the previous value and the second variable's value to the node's value. And then we did previous is equal to node, then we traversed the binary tree and right side, then we called our function value, and then we swapped the values which we have got. What this condition of if will do is that for the first encounter of the swapped variable, it will assign first to previous, and for the second encounter, the second time we got the swapped node, it will initialize the second node to the second node, and in this way we are going to get the full function to be ready. Now let's run this code. I think I have spelled wrong here. Let's now go and run it in our LeetCode. So here we have our LeetCode. We will paste it over here. Now let's run our code as we have pasted it. And we got our accepted input, and we got both the test cases to be passed, and our runtime was 0 millisecond. Now let's submit it and check what is the result. Yeah, we have been accepted, and our runtime was 6 millisecond after submitting our code. It's a pretty nice way. I think this is the best approach to solve this problem. So I hope you like this video and you got to understand how the algorithm works. If you want me to make the full video on binary search trees, what are they and how they work, you can comment down. Thanks for watching, and we will meet in the next video.